In the first talk, I was discussing voting rules, which are sometimes called social choice functions. Now I want to talk about social welfare functions. And the main reason for the change in focus is that Ken Arrow, in his original social choice formulation, worked with social welfare functions rather than with social choice functions. It turns out that it doesn't make a huge difference to the results. And if there's time at the end, I will talk about the voting rule formulation, the social choice function formulation. But because Arrow used social welfare functions, I'm going to do that too. Now, of course, Arrow didn't believe that society actually has preferences. In a social welfare function, a profile is mapped to a social ranking of alternatives rather than just picking out a winner. In the social ranking, we shouldn't think that society has a utility function or anything like that. The reason for ranking alternatives socially was purely practical. It's a contingency plan. You may not know in advance which alternatives are feasible. So if you rank all of the alternatives, if the top choice turns out not to be feasible, you can go to the second and so on. Now, you all know that the central result that Arrow derived was an impossibility theorem. If there are 3 or more alternatives, there is no social welfare function which satisfies the following axioms. Now, one was not explicitly stated by Arrow, but it's implicit in the formulation, which is ordinality. Arrow allowed individuals only to send in their ordinal rankings and not any additional information. There was an unrestricted domain condition. I'll talk about that in a minute. Pareto principle, which we already saw, non-dictatorship, which is a very weak form of anonymity, and Arrow's version of IIA, which I will spend a bit of time on. Just to come back to ordinality for a moment. So he demanded that the social ranking should just depend on individuals' ordinal preferences. In my first lecture, I showed you that you can derive ordinality from strategy proofness. Now, Arrow did not impose strategy proofness. He simply assumed ordinality. And this was coming out of a tradition that went back to Lionel Robbins. In the 18th and 19th century, it was quite common, both in economics and philosophy, to use cardinal utility. In fact, the great proponent of cardinal utility was Jeremy Bentham, who put forward utilitarianism, which is very much a cardinal philosophy. Robbins rejected all that because he said that there isn't anything scientific about cardinal utility. There's no way, if someone claims that these are my cardinal utilities, that you can test that. By contrast, you can verify ordinal preferences. If someone says that she ranks X above Y, there's a test that you can perform, an experiment you can perform. You can give her a choice between X and Y and see which one she chooses. If she chooses X, then indeed she does rank X above Y. There's no corresponding experiments with cardinal utility. except in the case of risk preferences. You can give people lotteries to ascertain their risk preferences. But if we're talking about a choice situation which doesn't involve risk, then risk preferences aren't germane anyway. So for that reason, Robbins and many subsequent writers, including Samuelson, including Arrow, rejected cardinal utility. Still, as I will be talking about in a little while, even if we're not looking at cardinal preferences directly, it may be possible to make inferences about cardinal preferences from ordinal rankings, which Arrow did not allow, but perhaps he should have allowed. So let me review the other Arrow axioms. The unrestricted domain just means that our social welfare function should be defined for all logically possible preferences and individual preferences. And again, I'm going to rule out individual indifference. I'm going to say that people always have strict preferences, but I'm going to allow any strict preferences. The Pareto property we already talked about. If everyone prefers X to Y, then X should be ranked above Y socially. And non-dictatorship says, in effect, that there's no individual who always gets her way. There's no individual who, if she prefers X to Y, guarantees that X will be socially preferred to Y. Now, UP and ND are all very weak conditions, so weak that they're satisfied by just about any social welfare function which is studied in practice, which is studied in theory or used in practice. For example, plurality rule satisfies these three conditions. We can think of the plurality rule social welfare function as one in which X is ranked above Y if more people rank X first than rank Y first. But practically no social welfare functions satisfy IIA. Now this is a different version of IIA from the one I was talking about in the first lecture. Arrow's IIA says that in determining the social ranking of X and Y, we should look only at individuals' preferences between X and Y. So in the Arrow formulation, we're fixing the set of alternatives. We're not throwing out alternatives as Nash was doing. The set of alternatives is fixed, but when we're determining the social ranking of X and Y, we're not looking at how individuals rank other alternatives. Now, one social welfare function that does satisfy this version of IIA as well as Nash's is majority rule. But the problem, of course, with majority rule is that it violates the unrestricted domain condition, because unless we restrict preferences, say, to be single peaked, we can get preference cycles, which in the Arrow formulation means that the social ranking is not transitive. It's not actually a ranking. It's a cycle. But despite the fact that IIA is so strong, it does have a compelling justification, very similar to the one that I was proposing in the first lecture. It rules out vote splitting and spoilers. And let me show you why the Arrow IIA condition rules out vote splitting and spoilers, just as the Nash one does. So this is the same scenario that we were talking about in lecture 1, Trump, Rubio, Kasich election, in which if we were using plurality rule, Trump would win because he has 40% of the votes, but a majority of voters actually prefer Kasich. Now, the reason Kasich loses under plurality rule is that Rubio, in effect, spoils the election for Kasich. He splits off some of Kasich's support. He splits off some of the first place votes that Kasich otherwise would have had. Now, Arrow's IIA rules this out, and let's see why. Here's another scenario in which these middle voters have now changed their preference, and now Rubio, who was on top, is now at the bottom, and Kasich and Trump move into first and second place. In the second scenario, pretty much any social welfare function we could imagine is going to rank Kasich above Trump, because Kasich is in first place 60% of the time, and in second place 40% of the time, and just the opposite is true for Trump. So any reasonable social welfare function is going to put Kasich above Trump. But if we impose IIA on our social welfare function, then we have to put Kasich above Trump in scenario 1, because the ranking between Kasich and Trump has not changed when we go from scenario 2 to scenario 1. We haven't changed anybody's preference between Kasich and Trump in going from scenario 2 to scenario 1. And therefore, if Kasich was ranked above Trump here, Kasich must be ranked above Trump in scenario 1. That is a prime justification for IIA. IIA rules out spoilers like Rubio. But I would argue that IIA is too demanding. Yes, it does rule out spoilers, but it's stronger than necessary for that purpose. And furthermore, it's so strong that it rules out taking account of preference intensity. And to make that point, let's look at another pair of scenarios. This is another scenario that we looked at in lecture 1. There are two groups of voters. 45% have the ranking XCY, 55% have the ranking YXZ. If you do the Borda count calculation, you'll see that that X comes in first, Y comes in second, Z comes in third. Now let's compare that with scenario 4, which is the same as scenario 3, except that now Y has moved up into second place in the first group of voters. So Y was at the bottom in scenario 3 for the first group, but now it's in second place. Now it turns out that Y is the top ranked alternative, and X is in second. This is a violation of IIA, because in going from scenario 3 to scenario 4, or from 4 to 3, the social rank, the way that group one ranks X and Y haven't changed. In both cases, X is ranked above Y. But the social ranking has changed, and that's the violation of IIA. Now, what's so bad about this violation? Well, it's harder to make the arguments that Z is a spoiler in scenario 3, because notice that in scenario 3, Z doesn't split any first place votes with Y. Z is at best ranked second. And so the strong argument we were making against Rubio in scenario 1 doesn't apply to scenario 3. So we can't justify Arrow's IIA on anti-spoiler grounds. And furthermore, there's a sense in which Z's position in group one's preferences is providing some useful information about the group one people's preferences. Notice that in scenario 3, Z lies between X and Y. That suggests that there may be a substantial intensity gap between X and Y. And I'll give you a formal reason for thinking this in a minute, but just go along with me for the moment. In scenario 4, notice that Z does not lie between X and Y. It lies below X and Y. And so that suggests that the preference gap between X and Y for the group one voters is smaller. And if you accept those statements, then we oughtn't to treat scenario 3 and scenario 4 the same way, which IIA would insist that we must. So that's an argument against IIA. Now, how do I make sense of intensity? Well, let's imagine that we're outside observers. We can't actually observe people's utilities, but from our point of view, let's imagine that these utilities are drawn from some set in an IID way. Well, then we can make inferences about these utilities based on ordinal rankings. The utilities themselves are cardinal, and they reflect the individual's preferences. We don't observe the utilities, but we know that if Z lies between X and Y, then the conditional mean of UX minus UY is bigger than the conditional mean of UX minus UY if Z does not lie between X and Y. And that's the sense in which we can make inferences about intensities based on ordinal information. Arrow did not allow for that because he had such a strong IIA condition. But we could imagine relaxing IIA so that we could make intensity inferences. Let's do that. Let me propose what I'll call modified IIA, which says that if there are two profiles of preferences, and we're looking at two alternatives, X and Y, if it's the case that each individual ranks X and Y the same way in both profiles, and it's the case that each individual ranks the same set of alternatives between X and Y in both profiles, then we rank X and Y the same way socially for both profiles. Now, if we just imposed premise 1, then this would be ordinary arrow IIA. But if we also impose condition 2, premise 2, then we do allow preference intensities to matter. Because we're distinguishing between the case where Z lies between X and Y, as in scenario 1, from the case where Z does not lie between X and Y in scenario 4, where the conclusion of modified IIA obtains only when in both scenarios Z has the same position vis-a-vis X and Y. And since in scenario 3 and scenario 4, Z has different locations vis-a-vis X and Y, modified IIA does not require the social ranking of X and Y to be the same. So with modified IIA, we do get the ability to take into account preference intensity, and we can still rule out spoilers, because if we go back to scenario 1 and scenario 2, remember that with plurality rule, Trump won in scenario 1, and Kasich wins in scenario 2. But if the voting rule satisfies modified IIA, then if Kasich is the winner in scenario 2, Kasich must also beat Trump in scenario 1, because in neither scenario 2 nor scenario 1 does Rubio come between Kasich and Trump. Rubio is ranked below Kasich and Trump in scenario 2. Rubio is ranked above Kasich and Trump in scenario 1. And therefore, the conclusion of modified IIA does apply to scenario 1 and scenario 2. But the social ranking of Kasich and Trump has to be the same in both scenarios.
Eric?
Yes.
Eric, there's a question coming from two people that asks, why wouldn't you, if you want to reflect really intensity of preferences, wouldn't you want to formulate this modified axiom so that there is the same number of alternatives between X and Y in both profiles?
That would be a stronger condition. So we could do that, but as stated, modified IIA is an even weaker condition than that, and my view is that the weaker the condition, the better. So
I guess the question would be, the rationale for modifying IIA was to reflect the intensity of preferences, so which IIA does not. But I mean, if your starting point is IIA and you say, well, I criticize IIA because it doesn't reflect intensity of preferences, but I want to stay close to IIA, then I guess that's the motivation for the question, that yes, you would pick a stronger version that just talks about the number of alternatives. But I mean, I think that's the question. I'm not saying that you might want to defer it to the end, or.
Well, what I would say is let's use all of this is going to lead up to not an impossibility result, but to a unique characterization of the Borda count. It turns out that if we replace IIA with MIIA, and if we introduce the May axioms for majority rule, then instead of getting impossibility, we get the Borda count. If we do that with this version of MIIA, a fortiori, we can get it with the stronger version of IIA.
Okay, very good. Very good.
So it's just on logical grounds that it makes sense to use the weaker condition.
Okay.
So I just referred to May's axioms for majority rule. I talked a bit about these in the first lecture without saying exactly what they are. So May was concerned with the case of just two alternatives, and he showed that majority rule is the only social welfare function that satisfies anonymity. If you permute individuals' preferences, you get the same social ranking. Neutrality, if you permute the candidates, the alternatives, you get the same permutation of the social ranking, and positive responsiveness, which is in the two alternative case, positive responsiveness is the same as strategy proofness. It's actually weaker than strategy proofness for more than two alternatives. So positive responsiveness says that if X rises and Y falls in individuals' preferences, and we hold all of the other alternatives constants, then X does not fall relative to Y in the social ranking. And if they were tied before, if X and Y were socially indifferent before, now X is strictly above Y. So those three conditions in the two alternative case are May's characterization of majority rule. Now let's look at those same axioms for more than two alternatives, and here is the main result. And now that you've seen this, Bob, you can leave without missing anything. If a social welfare function satisfies the May axioms, anonymity, neutrality, plus positive responsiveness, plus the arrow axioms, unrestricted domain, modified IIA. So it's not exactly arrow, it's a weaker form of arrow. Then the social welfare function must be the Borda count. Now, there are two other arrow axioms, non-dictatorship, but that's weaker than anonymity, so we don't need that. And Pareto, we also don't need Pareto for this result. And in the rest of this lecture, I'm going to spend some time trying to show you why this theorem is true. The argument is not quite as simple as the proof of the main theorem in the first paper, but it's simple enough so that I think you can get the main idea. And to do that, I'm going to concentrate on the case of three alternatives. Two alternatives was already settled by May. Notice that the Borda count and majority rule are the same for two alternatives. So it's only when there are three alternatives or more that that you get a difference. Let me start out by imagining that people's preferences were restricted to this triple of orderings, XYZ, YZX, ZXY. So this is the same Condorcet cycle that I was ruling out for majority rule in the first lecture. Now let's imagine that the population splits into three equal groups. 1/3 of the population has the ranking XYZ, 1/3 ZXY, 1/3 YZX. Suppose that we have a social welfare function that satisfies our axioms, the 5 axioms. I claim that the social ranking for this profile must have X and Y indifferent. So why is that? Well, if we don't have indifference, then we have some strict preference. Perhaps X is strictly preferred to Y. So suppose that X is strictly preferred to Y socially. Now what we can do is to look at a permutation. I talked about doing this in lecture 1. So let's look at the permutation where X is transformed to Y and Y is transformed to Z and Z is transformed to X. If we apply that permutation to this profile here, we get this profile. This is the transformed profile. And now we have Y is ranked above Z. We can infer that from X is ranked above Y over here. Let's apply the permutation once again. And now we have Z ranked above X for this profile. But if you look at the profile in 3 and if you look at the profile in 4, you'll see that they are just permutations of voters from the profile in 2. We have exactly the same rankings. It's just that different people have those rankings. And so from anonymity, we can conclude from 2, 3, and 4 that for this profile, the social ranking must be X above Y, Y above Z, that's from here, and Z above X. But notice that this is not transitive. That is, we don't actually have a social ranking. We have a violation of transitivity. And so this strict social ranking couldn't have been possible in the first place. We would get the same contradiction if the social ranking went the other way, Y over X. The only possible social ranking for this profile is social indifference. But we can go farther than that. We know that if for this profile A equals 1/3 and B equals 1/3, we have social indifference. We just proved that. But if we change A and B so that they add up to 2/3, we still have to have social indifference, and this is because of modified IIA. Notice that as we change A and B to keep their sum constant, we are changing the profile so that Z never lies between X and Y. Sometimes it lies below X and Y, sometimes it lies above X and Y, but as long as we never change things so that it lies between X and Y, we can conclude that we still must have indifference. social indifference. Furthermore, if we increase the sum of A plus B so that now it's more than 2/3, that allows us to conclude from positive responsiveness that now X must be ranked strictly above Y, and if A plus B is less than 2/3, Y must be ranked strictly above X. So we now know a lot about our social welfare function. In fact, we know exactly what the social ranking will be for any profile, because these three cases cover all possible profiles. Not only that, we've shown that the social welfare function must be the Borda count, because the Borda count has exactly these social rankings. That's easy to check. For example, in this profile, the Borda score for X is 3A. A is the fraction of voters who put X first, so X gets 3 points for all of those voters, so there are 3A points there. And X is ranked second by fraction B, so we add 2B for those voters, and it's ranked third by 1 minus A minus B voters. And so this 3A plus 2B plus 1 minus A minus B is the total Borda score for X. And similarly, the total Borda score for Y is this expression here, 3 times the quantity 1 minus A minus B plus 2A plus 2B. But if you simplify these expressions, you find that X is ranked above Y strictly if and only if A plus B is greater than 2/3. In other words, we have completely characterized the Borda counts using our 5 axioms: unrestricted domain, modified IIA, anonymity, neutrality, positive responsiveness. Now, so far I've only done this for the case where preferences are restricted to be this to lie in this Condorcet cycle. So we have to extend the argument to the case where all possible rankings of X, Y, and Z are possible. So let's do that. If anyone is interested, I've written out the conditions more formally, but I think I will skip that for now in the hope that the informal definitions were clear enough. So,
Eric?
Yes.
There's a question coming in. You might want to defer it to the end. What happens if we drop anonymity?
Oh, well, if you drop anonymity, then for example, you could do a weighted Borda count. So in the Borda count, all individuals count equally, but if you did the same thing as the Borda count, but you you gave more weight to one individual than another, then that would be allowed too. Mm-hmm. So you set of weighted Borda counts if you dropped anonymity. Okay, so let's look at the case where we allow for all preferences, not just the Condorcet cycle preferences. And remember, I'm restricting preferences to be ordinal. So this is my notation for a profile now. I had U dot in the first lecture where we were in principle allowing for cardinal utility, but now with ordinal utility, I'll use this ordinal preference notation. And to make the argument, let's first define AXY for a profile to be the fraction of individuals for that profile who rank X above Y and don't put Z in between. So it's the fraction who either have the ranking XYZ or ZXY. And we can similarly define AYX to be those who rank Y above X without Z in between. And then there's the fraction who do put Z in between. So AXZY is the fraction with the ranking XZY. AYZX is the fraction with ranking YZX. Now, for any profile, we only have to know these four numbers in order to deduce what the social ranking is. So they're in effect a sufficient statistic for the profile. If we didn't impose modified IIA, if we just imposed anonymity, then we would need 6 numbers because there's 6 possible strict rankings, and so we would have to know the proportions having those 6 different rankings. But because of modified IIA, it doesn't matter whether someone has the ranking XYZ or ZXY from the point of view of the social ranking of X and Y. So we can get it down to 4. Now, suppose we have a particular fraction of people, alpha XY, who rank X above Y, and another fraction who rank Y above X, and neither group puts Z in between X and Y. Then we can define what I'll call I of alpha XY, alpha YX, as the fraction of people with the ranking XCY needed to get society to be exactly indifferent between X and Y. So we first fix alpha XY and alpha YX, and then we calculate what must alpha x c y be in order for this this four-tuple to lead to social indifference between x and y. It may be that there's no value of alpha x c y for which you get social indifference. For example, if alpha x y equaled 1, if everybody preferred x to y, then there's no way that we could make society indifferent between x and y. But when it is possible to find a value of alpha x z y such that we get social indifference for this four-tuple, that's the case that I'm interested in. We'll define I to be the value of alpha xcy, which produces indifference. So we can think of this curve as a function of alpha xy, alpha yx as the social indifference curve in proportion space for x and y. And what I want to do is to show that this social indifference curve must coincide with the Borda social indifference curve. Now, what is the Borda social indifference curve? I claim it's this. And actually that's very easy to derive, because if we're comparing the Borda scores for x and y, notice that if z is not in between x and y, then if someone ranks x above y, x gets one more point, one more Borda point than y. And if someone ranks y above x, y gets one more Borda point than x for each such person. So this difference here corresponds to how many additional points x gets compared with y when we're just looking at preferences where z does not lie between x and y. Now, for the preferences where z does lie between x and y, then every time x is ranked above y, x gets 2 more points than y. So that's why over here, there's a 2 multiplying IB, which is the fraction of people with the ranking XCY. And over here, we have this number here, which is just what's left after we look at alpha XY, alpha YX, and IB. This is the fraction corresponding to people who rank Y above Z above X. So this total expression is the difference between the Borda scores for X and Y. We can now solve for IB, and we just get this expression here. So our proof will simply consist in showing that if F satisfies the 5 conditions, it has an indifference curve that looks like that. Now, to do that, let me assume that the indifference curve is linear. If it's nonlinear, the argument is more complicated, and I will get to that later. But for now, let's assume linearity. So that means that I takes this form here, b naught plus bxy alpha xy plus byx alpha yx, where the b's are constants. Now, one case where we can clearly make inferences about the form of the social indifference curve is where alpha xy equals alpha yx. Why? Because in that case, the number of people, or the fraction of people who have the ranking x, z, y must equal the fraction of people who have the ranking y, z, x. Simply from symmetry. If we have the same number of people with the rank who rank x above y as y above x, when z is not between x and y, then we must have the same number of people who rank x above y as y above x when z does lie between x and y. So this is simply from the fact that anonymity and neutrality impose some symmetry on the social indifference curve. We can also make some inferences about the social welfare function from this profile. Now, when there are three alternatives, there are six possible strict rankings of the three alternatives, and they're listed here. Suppose that we look at this profile where C is a constant. We're going to vary C in a minute, but for the moment, C is a constant. What we've done here is to break up the six rankings into two Condorcet cycles. So these preferences here are one Condorcet cycle, and these three preferences over here are another Condorcet cycle. And we can go through essentially the same argument that I made before for the Condorcet profile to conclude that for this profile here, the social ranking of x and y must be indifference. It's the same set of steps leading to intransitivity. If we had strict preference, we would get intransitivity for this profile for exactly the same reason as the previous argument provided. But that allows us to conclude that the social indifference curve must have this form. Now, where does this come from? Well, this first number, 1/3 plus 2c, is the fraction of people who rank x above y when z does not fall between x and y. Now, that corresponds to these people here, and these people here. In this case, z is below x and y. In this case, z is above x and y. So the total fraction here is 1/3 plus 2c. That's where the 1/3 plus 2c comes from. Now, the argument here is alpha yx. That's the fraction of people who rank y above x and also don't put z between x and y. And that's these people here and these people here. And that adds up to 1/3 minus 2c. And since we have since we know we have social indifference for this profile, that means that the fraction of people with the ranking xzy must be the same as for this profile. Now, notice that these are the only people in the profile who have ranking xzy. So that means that that's what the social indifference curve must give us, exactly this fraction here. But notice that we now have two linear equations and if we go back to the if we go back to this equation, we have two linear equations. We have three unknowns, b naught, bxy, byx. So those three unknowns are determined uniquely from these two relationships. And that's really all there is to it for the case of three alternatives. Now we can extend this argument, assuming linearity, to more than three alternatives. We can proceed iteratively using the fact that if there are just three alternatives, I must have this form. We can deduce that it must have the corresponding form when there are four alternatives, and going from 4 to 5, the same kind of argument applies. Repeating this machinery as many times as needed, we can show that this holds for any finite number of alternatives. The more complicated step is to see what happens if the indifference curve is not linear. If it takes a polynomial form, then it turns out that essentially the same argument that I showed you will continue to apply. So suppose that I were a quadratic rather than linear. What you can show is that for a situation like this, as you vary c, all of the constants for the nonlinear terms must be 0. So the polynomial, the nonlinear but polynomial argument is really just an extension of the argument I already showed you. What is still open, and I'd be interested if any listeners had ideas about this, is how to extend the argument to the non-polynomial case. That is still open. There's a sense in which it's a very small gap, because any nonlinear, non-polynomial curve can be approximated arbitrarily closely by a polynomial curve. So practically speaking, this is not an important open case, but mathematically, it would be nice to settle. So the non-polynomial case is still open. And then the final thing I want to point out is that we can also extend the argument to voting rules. So as I said, Arrow required that you get a social ranking of all alternatives, whereas with a voting rule, the interest is just finding out who won. But the same sort of argument that I was giving for social welfare functions easily extends to voting rules, since we're only interested in comparing two alternatives at a time. So either X gets chosen or Y gets chosen. The same arguments that we gave in the social welfare function case can be applied to the voting rule case to cover voting rules. And with that observation, I think I will stop and open it up for questions. Oh, actually, I do want to give the big picture moral from these two lectures. So in the first lecture, I was arguing in favor of majority rule. The emphasis in the first lecture was on strategy proofness. In the second lecture, I was arguing for the Borda count. The emphasis in that lecture was on accounting for preference intensities. So there's a clear-cut sense in which majority rule is the method we want to use when we care about strategy proofness. Borda count is the method we want to use when we care mostly about preference intensities. Unfortunately, and this is going back to Arrow once again, we can't have both at the same time. So we make a choice, one or the other. Condorcet and Borda dominate everything else, but they don't dominate each other. Each has its uses depending on the circumstance, and that's the moral of the story, if you like. Okay, let me stop there and take further questions.
Okay, I'm going, Eric, thank you very much. This was very interesting. I'm going to unmute everyone.
אמרתי את זה, לא שאלו אותי, לא יודע, אבל אני אגיד את זה, זהו, אז אני... תראה, אמרתי... כן, כן, כן. כן, כן.
Okay. There was a question related to the... When you drop anonymity, you mentioned that...
אמרתי את זה היום במחלקה שלי. אמרתי שאני מבין, כמובן, למה יש מעט יותר, אבל אני עדיין מעודד אותם לקחת תלמידים, כי זה...
I'm sorry, I'm not...
זה חשוב.
People talking at once, I can't hear the question.
I'm sorry, just a second. I'm muting back because there are no noises. Okay, so in the middle of the talk, there was a question about what happens when you drop anonymity. You said that one class of rules would satisfy your axioms would be weighted Borda rule, and the question is that the only class, or?
Yeah, so
do you know?
Whether you could have weights, so certainly if the weights are fixed, if the weights are constant, then that will satisfy all the axioms. Frankly, I haven't checked to see whether the weights can be variable. That's also an open question.
Okay.
So I don't know the entire class.
Okay.
For anonymity is weakened.
Okay. Sergio wanted to ask a question. So Sergio, go ahead. I think you are unmuted now.
Okay. Oh, I was unmuted. Thanks. So, Eric, thanks. I mean, must be a real tour de force to give 2 lectures like this. Not so easy. So we really appreciate it. Here's my question. Suppose that I have an MMIIA, which is a modified IIA, that says IIA applies provided I keep the location of X and Y in the same place. I don't care about all the others, how they move. But if X was in place 3 and Y in place 7, then that should only depend on that. Now, there is a generalized Borda where you can give to every place a different weight, weight being monotonically increasing, of course, because of the May. You have the May thing that when things go up, it goes in the right direction, but the weights are fixed. So let's call, I'm still keeping anonymity and neutrality, which means that everybody has the same thing, but there is a Borda where you don't give n minus 1 and so on, but you give some weights, okay? Now, clearly that will satisfy that axiom. Question, are there other things?
I don't know. That's a good question.
Somehow I have a feeling, I mean, I'm not sure that your proof, the way you do it, will cover it. I think you will need some additional tricks.
Right.
But I have a feeling that may be a nice generalization.
Yeah.
And again, there are 2 ways to look at your modified. Do we want something that is as close to arrow as possible or as weak as possible, which are contrary directions? And right. you can do both things. So that's this. So that was comment number 1. Which,
so that's a nice conjecture.
Yeah, it's conjecture. Yes.
This result is that I haven't had a chance to explore all of these possible generalizations, but I'm very happy if other people do.
Yes. Okay. And now a small comment. You could add some continuity that says that once you have strict preference in the social decision, there is a small enough changes in the profile are going to keep that. Okay,
Yeah.
and I think that will take care of polynomials and continuity and all this thing in an easy way without having to work too hard.
Could be. So that,
I mean, it's not an axiom that is part of the standard ones, but maybe a good axiom. Why not? Again, that strict preference are preserved for. It's an open mapping. So strict preferences for small enough changes they stay. I mean, you could do the converse that greater equal in the limit it becomes greater equal. I mean, there are various ways to do it, but you get some continuities, which means that when you change your alphas slightly, then nothing. Then you keep.
yeah. So here is my doubt. We're working with the indifference curves. Suppose the indifference curve were a polynomial rather than a linear curve. The regions where you had strict preference would still be nicely behaved. And so you should be able to do the sort of permutation of alphas that you're talking about. I don't quite see why moving from lines to polynomials is going to introduce discontinuities.
No. My point was how to handle, once you have polynomials, how to handle arbitrary functions. That's all. An easy way to get the last step of the proof. That's it.
Yes, right. I see. Right.
That's all. That's all I said.
Okay. No, you're right. You're right about that. You can approximate any arbitrary function with.
Now, again, the approximation is on a different level, which you have to see. It translates. I mean, it's not so easy because the translation from profile to the indifference function is not direct, and you have to see that it goes right. But I expect that it should work. That's all I'm saying.
Now, somehow, I have the feeling that there must be a more direct way of doing it. I have given some thought to.
Okay. How about another thing I was thinking? Don't you really? This is really looking locally. When you look locally, what matters is just the slopes somehow. And so you can. But again, I still have to understand the proof better. But I got a feeling that that's really what matters are slopes. And if it slopes, then again, then it's a linear approximation. Again, something. In
that's right. Now, I should say, and this is another area in which it would be nice to generalize that this argument, the one I've shown you today, relies very heavily on there being a continuum of people. Because I'm varying the proportions in a continuous way, as you were saying, Sergio.
Yeah.
For the first results, for the first paper, the first lecture I gave, I was also using a continuum, but in a less sense.
To rule out.
Yeah. Everything I said for generic profiles, in the first paper, I could have said for profiles with high enough probability in a finite setting. For the second paper, I'm not so sure. That is, it may be that the continuum is more important to the conclusions than in the first paper. That still needs to be worked out, and what you get when there are only finitely many voters.
No, for any finite number, surely.
Sergio, I'm afraid I have to interrupt because there are other questions.
Okay, I'm done.
Andy, you had a question? Please go ahead.
Okay, I have two questions. One is just one about following your talk, which is just can you refresh when these two methods or what kinds of situations these two methods give different answers, or a simple characterization of when they give different answers? That's the first question.
When Borda gives a different answer from Condorcet, you mean?
Yes.
Oh,
Are those obscure situations?
so in the very first example I gave of Borda, where there were 45% of the people who had ranking, actually it's probably easiest if I go back to that. Let me. So here, in scenario 3, the majority winner is Y.
Yes.
The majority of people put Y first, but X is the Borda winner because
Right.
because Y is way down at the bottom for this first.
Let me ask a different question. So you don't explicitly talk about it, but in the background, you kind of, it seems like you have in mind a distribution of distributions, which is in the world of possible ways that people can vote. And you know, like when you say majority rule works pretty often, do you have like a sense of how often these, you know, in the kind of distributions you expect in elections, how often these different things go bad?
Okay,
Yeah.
that's a very good question. There are two ways, at least two ways, of trying to answer such a question. One is to make a theoretical calculation. Suppose that we were, suppose that there are just three alternatives, and we're choosing preferences at random from the 6 possible rankings of the 3 alternatives. We're calculating, and let's calculate how many times there's no majority winner. Or what is the probability of there being no majority winner? It's a little under 8%. So about 92% plus of probability of there being a Condorcet winner. But that actually overstates the problem. Preferences are much more highly correlated than an IID draw would suggest. And so what we can do is to look at an empirical answer. There are places in the world where people have been, where countries have been using ranking voting methods for many years now. Australia is an example. We have 100 years of data on elections that have been taking place in the lower house of parliament in Australia. So we have 100 years of rankings. We can see from those rankings how often we don't get Condorcet winners. And I actually have a student who he wasn't looking exactly at that question. He was looking at something else, but he looked at all elections in the lower house between 1992 and the present. So that was about 1,500 elections, 1,500 seats in the House, and there was not a single example of a failure for a Condorcet winner to exist. So they always existed. Now, actually, in a lot of those, there was not just a Condorcet winner, there was a plurality winner. I was saying that the problem with plurality rule is that you have vote splitting and you have spoilers, but that actually happens only in about 15% of cases. In most cases, plurality rule actually coincides with majority rule. So the conclusion we get from the empirical evidence is that majority rule works fine in just about every case. But plurality rule works fine except in about 15% of the cases. So we're making an improvement by moving from plurality rule to majority rule, or from plurality rule to Borda count, but only in about 15% of the cases is that a real improvement.
Can I ask another question? And if it's too long a question or too, skip it, which is that all the, some of the details, I guess, are interesting mathematically, but there's a lot of weight, it seems like, being put on what the low parts of people's preference lists. And, my experience as a voter is that once I get past the first two, I'm kind of just guessing my way down the list.
Oh,
and
yes.
Like you want to put, if you added if you said people have a real preference list, but they don't know what it is.
That's right.
Low parts of the list,
That's
they
right.
know what they're talking about. Like runoff election is a natural thing to put into voting to fix that.
So again, that is an excellent point, and let me say that for any voting rule which involves ranking, which includes majority rule and Borda, and instant runoff voting and a number of others, it's very important that you give voters the option of not ranking all candidates. So what you want to do is to allow them to rank some, but not all of the candidates. And that means that the ones who are not ranked are considered as tied at the bottom. Now you can even go further and say, well, I know that I like X more than Z, and I know that Y and W are in between, but I can't rank Y and W, so I will treat them as indifferent. I think it's valuable to allow voters to express indifference whenever they want. Now that actually, so for the first paper, the majority rule paper, I know that allowing for indifference is not going to affect any of the results. But again, it's an open question. How allowing for individual indifference will affect the Borda count results. I don't yet know the answer to that. And I'd be delighted if other people wanted to get into the act.
Arsen Ivanov, you had a question?
Yeah, hi. I want to ask, you proposed an argument for relaxing IIA that was about preferences being based on randomly drawn utilities.
Yes.
Does that argument rely on information in utilities beyond cardinality, some kind of interpersonal comparability?
I didn't catch the last part. You were saying something about interpersonal something?
Yes, does the argument rely on information in utilities beyond cardinality? Maybe some kind of interpersonal comparability of utilities?
So I was assuming nothing about interpersonal comparisons for this result. I relaxed IIA to allow individual intensity, and as a theorem, but not as an assumption, we did get some interpersonal comparability, because the Borda account does make some interpersonal comparisons, but that was not assumed. It was an implication.
Just the argument, the justification for relaxing IIA, the axiom IIA, the argument there were some utilities in the argument. It was an informal
There were
argument.
utilities in the argument, but there was no interpersonal comparability.
Okay, but then can we make?
Okay, so there's been a long debate. So I argued, or actually, this really all goes back to Lionel Robbins. Robbins started a reaction against cardinal utility and also against interpersonal comparability of utility, because he said in both cases there is no scientific experiment we could perform to validate these comparisons. Now, I think he was just wrong about the first. It turns out you can make statements about intensity, about cardinal utility, if you're willing to make some additional assumptions about where these utilities come from. So I showed that if you're choosing utilities from a distribution, then you can make inferences about cardinality from just ordinal information. But that doesn't, that still doesn't give you a way of making inferences about interpersonal comparisons. There is no obvious experiment we can perform which will lead to the conclusion that I are more about X over Y than you do. There's a debate, of course. I mean, this is controversial, and ever since Robbins made this very strong statement about no interpersonal comparisons, people have been pushing back. But I think it's fair to say that it is controversial, and perhaps the less that we assume we can do in the interpersonal comparability arena, the safer the ground that we will be on.
So could we make your argument purely based on risk preferences? Or are we using information that is somehow beyond the cardinality, the utilities?
We could not do it on the basis of risk preferences, because we're talking about choices that may not involve any risk. Risk preferences only come in if our choices are genuinely, if our preferences are genuinely risky. It would be a mistake to say that because I'm risk averse when it comes to alternatives X, Y, and Z, that we should choose X rather than Y. I think that's faulty logic.
just last remark. I'm just trying to establish whether this argument behind relaxing IIA involves anything other than reviewed preference. The argument is made in terms of utilities. Can it be made in terms of reviewed preference, or is there more in there?
It's assumed, the argument was assuming that people do have intensities, but we can't observe them directly. And then yes, we can infer those intensities from revealed preference, from ordinal rankings. And that's all.
Sergio, you had a final, there was still a question that you wanted to ask?
No, just no. I just want to say that the comparison comes through anonymity. That's it. The interpersonal comparison comes through anonymity. That's all you get.
Yeah, no, that's right. It means that if I stick Z in between X and Y, that has the same, anonymity means that if I do that, it has the same effect as you're doing that.
Exactly. That's it.
So that is the interpersonal comparison.
Well, I guess one could view it as saying, since we don't want to make interpersonal comparisons, we want to consider all individuals as equal. That I wouldn't, yeah, I don't want to dwell on it too much, but I'm suggesting a different way to say we want to avoid interpersonal comparisons, and hence we are treating individuals as the same. It doesn't mean that. I think it's somewhat different, no?
I'm not quite sure what you're saying. So anonymity is
Anonymity does not necessarily mean that we think that there isn't really in the world a difference between the strength. I mean, in many cases, we do make judgments about the intensity of the need of one individual versus another individual. And not only we make these judgments, but there's a rather broad consensus, like in medical treatment, that the need of one person for a certain treatment is stronger than the need of the other.
That's right, and that will be that, formally speaking, is a violation of anonymity. It means that we have additional information outside the voting framework, which allows us to distinguish one person from another. But in a political setting, where we're all voting for president or all voting for MPs or whatever, there is a long tradition, long assumption that all citizens will be treated equally, and just because I'm more needy than you doesn't mean that I have more weight
and more right. Yes, have a strong claim
in the political system. So that
I don't have a stronger claim, even though I might prefer one candidate upon the other much more intensely than you do. It doesn't.
Yes, but that
doesn't mean I have a stronger claim. I don't have a stronger claim.
But the fact that you prefer one candidate much more intensely than I do can be ascertained indirectly through the other candidates that you put between those two.
But I think there is a mix-up here. I think there is a mix-up between two things, Elchanan. Again, exactly the MIIA shows you that if the distance between X and Y is 1 in your ranking, it doesn't matter if they're at the bottom or they're both at the top. It's just the distance between them. So that's very different than saying if you are poor, getting $1 more is worth much more than when you are rich. So being on the bottom and going up by 1, or being on the top going up by 1, it's the same. That's what MIIA says. Okay, and you are taking it in a different direction, which is not consistent with that.
No, but another thing Elchanan was saying is that we may know that that you are rich and Elchanan is poor, which is information in addition to your preferences, in addition to your utility functions, and we may use that additional information to decide on who gets what. And,
yeah, but that will be the non-anonymous Borda, weighted non-anonymous Borda, for example.
Well, maybe.
For example, I said for example.
It might, yes, that's right. The non-anonymous Borda would be one way of taking care of that, but there might be other ways.
Definitely.
We might use a Rawlsian way. So we might decide that we want to allocate things to the poorest person first. That we put most priority on that. So lots of things become possible once we non-anonymize the allocation process. I have been avoiding that because my initial motivation, if you'll recall that from the first lecture, was political elections. But of course, all of these rules can be used much more widely than in just political elections. In which case, we might want to drop anonymity.
Okay, Eric, thank you very much for really very stimulating talks. And we're very grateful. And I want to try to unmute all of us so that we can clap hands. Thank you, Eric. And thank you all for participating in this. And Eric, we are looking forward to see you here again.
Yes.
In the summer school next year.
So this has been fun, but it's a lot more fun to do it in person. And
absolutely.
I look forward to that next year.
You know the saying, it's next year in Jerusalem. You know what? Any place where we can finally meet together.
but Jerusalem wouldn't be bad.
Thank you very much.
Bye, everyone. Thank you.
Thank you.
Thank you all. Thank you.
Thank you.